So we are done with the DC circuit analysis. Now taking up the AC circuit analysis, we'll be looking at different AC circuits. And now in AC circuits, we'll also be taking up the other two passive elements, the inductor and the capacitor, and also analyzing their behavior in an AC circuit. Uh, so we'll start with today, first of all, with an understanding of what a sinusoid is and what a phasor is. So first of all, the sinusoid, when we are talking about alternating voltage or alternating currents, these are those voltage or currents that actually are a function of time and they are varying sinusoidally with respect to time. So an alternating an AC current or an AC voltage is something that is varying sinusoidally with respect to time. So if this is your time axis, your x-axis is the time axis. From this side, I'm still. What we have with an AC circuit is that an alternating current or an alternating voltage is varying, is a function of time. It is not now a constant. It's not constant as we saw in case of DC voltage or DC currents. DC voltage, DC currents, they are constant. They have a fixed value. They do not. They are not a function of time. They do not change with respect to time. Whereas alternating currents or alternating voltage, they are not. They do not have a constant value. They are a function of time. They change with respect to time. Fine. So both AC voltage or currents, VT or IT, now they are a function of time, and they are being a function of time. One thing is being a function of time. Second thing is they are a sinusoidal function of time. Now, what does sinusoidal function of time mean? It means they can vary with respect to time either as a sine function or a cosine function. Right? So you have Vt. Uh, it will be a function of sine of t, or it will be a function of cos of t. As say Vt as well as it. It will be a function of sine of t as well as it is a function, or it's a function of cosine of t. It is varying, it is changing with respect to time, and it is changing sinusoidally with respect to time. Now, sinusoid is a signal that actually uh, takes up any of these two forms, either a sine function or a cosine function. Yes, it is visible. Can rejoin. So a sinusoid is any signal that actually takes either a sine function or a cosine function. Its waveform is actually either sine or a cosine. Right? So यहाँ पे जो मैंने function बनाई, it is simply a sine function. Now a sine function is something that actually starts sine of 0, actually 0. So it actually, or its value at 0 will be 0. Cosine function at 0, it will be having a peak value of 1. Cos of 0 is 1. So cos of, if you want to represent the same function with the cosine function, it will start uh, from a, it will take a value, it will vary like this. So you can now represent Vt or It, voltage and current, either as a sine function or a cosine function. Now these two functions are together, they are actually known as sinusoids. In DC, what we had a constant value. Now in AC, we do not have a constant value. We have voltage and current. One, they are a function of time, and two, they are actually a sinusoidal function of time. Therefore, Vt can now be represented by the form Vm sine omega t. In case of DCs, we are simply writing V is equal to 10 or V is equal to 20. Now here we'll be writing a function Vt equal to Vm sine of omega t, where omega t is will be this axis, Vt is your function, and it's varying sinusoidally. Vm is called as the magnitude, or you can say amplitude of this function. Omega t is the argument, or you can say simply the angle of this function, while as omega is your uh, angular frequency. The units of this are radians per second. Now alternating voltage will be represented by a sinusoidal function, uh, and the, the basic representation of any voltage is Vt equal to Vm sine omega t. As a sinusoid, we can represent Vt is equal to Vm sine omega t, where Vm is the magnitude of this function, omega t is the argument, and where in omega t, omega is actually the angular frequency. So as time actually changes, omega being constant, as time changes, your function will vary with respect to time in this sinusoidal manner. So ये जो peak value है or the amplitude, that is actually Vm here. Now you can see after every time period, let this be t, this function is actually repeating. So it's a periodic function having a period of t. Also, this time period t from this x, you can see time period t here is equal to 2 pi. Fine. So your function is now periodic. It's having a and it's periodic function with the time period of t. So you can say at omega t equal to 2, at omega t equal to after every interval of omega with a capital T, omega t equal to 2 pi, your function is repeating. So from here, you can say that your time period of this function is 2 pi divided by omega. Fine. So your time period after which every time period capital T, your function is repeating. So your function is now a periodic function having a period of time capital T equal to 2 pi divided by omega, where omega is the angular frequency of this particular function. Also, you already know that with the periodic function is also uh, associated the frequency f. F is simply given by 1 divided by t, capital T. Substituting this value, f will be equal to omega divided by 2 pi. Or you can also, so you have uh, f equal to omega divided by 2 pi, or omega is equal to 2 pi f. So we have taken a simple function Vt equal to Vm sine of omega t. This is the sinusoidal form of our voltage now, where you can see actually our function is varying sinusoidally with respect to time t. This function has a magnitude of Vm, magnitude or amplitude of Vm, It has an argument, or you can say the angle of omega t. So as your angle is varying, you can see your function is varying sinusoidally with respect to time. Your function is also periodic, having a time period of capital T. From this waveform, you can actually see that capital T is equal to 2 pi divided by omega. And if we want to find out the normal frequency of this waveform f, that will be given by omega equal to 2 pi. So f is equal to omega divided by 2 pi is the frequency of our periodic waveform. The units of frequency are hertz, as you know. The angular frequency of this particular waveform is omega, that is 2 pi f. The units of this are radians per second. The time period is given by 2 pi divided by omega. Simply in this represents the time after which, after every time period capital D, your waveform is repeating in nature. So these are some of the some important terms that you need to remember for a sinusoid. What's its frequency? What's its angular frequency? What's its time period? F is also having a relationship of 1 by t with the f is equal to 1 by t. F is having a relationship, this relationship with the time period, capital T. Now, as we have represented Vt as a function of time, Vt equal to Vm sine of omega t. Similarly, we can also represent current as a function of time, Im equal to Im into sine of omega t. Fine. Now, sometimes what you'll see is that your waveform, it is not necessary that your waveform starts from 0. Your waveform may start from, maybe it may start from here. Fine. So let this be V1 equal to Vm sine omega t. Now, if this angle here is represented by phi, then this function V2 will be represented by Vm sine of omega t plus phi, because if we substitute a value of omega t equal to minus phi here, then only sine this angle will become, this argument will become 0, and sine of 0 will be equal to 0. So you can see there is another function now here, V2, which is equal to Vm sine of omega t plus phi. Now for this particular function, Vm still represents its magnitude or its amplitude. Omega t plus phi represents its argument. Now phi specifically, it represents the phase of this particular function. So when we talk about phase, whenever we'll be talking about the word phase, what you can actually refer to is actually it represents that point from where actually your waveform is starting. Fine. Now, if your waveform is actually starting, uh, we have seen it is waveform is waveform of this particular function Vm sine of omega t plus phi. If you have a term plus phi here, that means it's actually already started. This function has already started. Therefore, we'll say that V2 is leading V1 by a phase of phi. Fine. If there is another function V3 equal to Vm sine of omega t minus phi, say for example, that means there is another function V3 here that is starting from plus phi. Fine. This is V3 equal to Vm sine of omega t minus phi. So minus symbol here represents that V3 is lagging what? V1 by a phase of phi. So I actually shown three waveforms here, V1, V2 and V3. All of these functions are sinusoidal functions. And when we are comparing three functions, make sure that the frequency of all of these functions are same. Frequency, that is frequency or angular frequency of the all of these functions is same. You can see frequency omega t, omega t, omega t. In all of these three cases, the frequency is same. Only then we can actually compare the three waveforms. Now you can see that V2 has already started, then V1 is starting. So we can say that V2 is leading V1 by a phase of phi. V3 is starting much later as compared to V1. So you can say V3 is lagging V1 by a phase of phi. You can also say that V1 is lagging V2 by a phase of phi. And also we can say V3 is lagging V2 by a phase of 2 into phi. ठीक है, V1 और V3 के बीच में भी एक डिफरेंस है, that is 2 phi. So phase is an important concept in AC systems because most of the times reference तो हम लेते हैं. We always take a reference having an angle of 0 degrees, but all other functions in the system will now, when we'll compare it with respect to the reference waveform, they will be starting from some different points, or they have already started. So all of those other functions will be having a particular phase. Now, whether those phases are leading, or those particular functions are having a leading phase or a lagging phase, that is very important in power systems or electrical engineering. So, uh, based upon these phases, we will actually be studying a number of important terms later on. Fine. So, this is the sinusoidal representation of an alternating voltage or of an alternating current. Okay. So what we have here is a simple sine function. You can also have a cosine function. I can also write V is equal to Vm cos of omega t. Fine. So if I write a function V is, now since we are writing functions, we should also always mention this in the brackets. Vt is equal to Vm cos of omega t, and the function will look something like this. Only difference between sine function and the cosine function is that at cos 0, the value is already 1, so it will already be starting with the amplitude of Vm. So this will be the difference between a cosine function or a sine function. Now you can represent your alternating voltage as well as alternating currents as a cosine function or a sine function. Now associated with the cosine and sine functions is frequency, is angular frequency, is the time period. So you need to know what is your frequency of the system, what is your angular frequency of the system, what is your time period of this system, and also you need to know what is the phase of a particular uh, function, right? Now the question comes, first of all, why we are actually having alternating voltage over DC voltage. So actually there are a number of advantages of using alternating voltage over DC. AC system has a number of advantages over a DC system. AC is much more easier to generate as compared to DC systems. AC systems, as you know, you may be having transformers. So what transformers do is they step up your voltage or they step down your voltage. सबके घरों में transformers होंगे, so you will be able to step up your voltage as per the requirements of your system. But there is nothing like a DC transformer. So DC voltage, whatever you will be receiving, you cannot step it up or you cannot step it down. There is no electrical machine that actually steps up or steps down a DC voltage. Uh, there was actually no such machine for a very long time. Now using power electronic circuitries, we are able to step up or step down DC voltage but that is secondary. For major jobs, actually we have been actually using AC systems for a very very long time. There was no such mechanism to step up or step down the DC voltage. So alternating voltage, because of those advantages of easy to generate, easy to transmit, easy to distribute, it was preferred mode of it has been preferred, and it is actually used uh, for most of your applications nowadays, residential applications or industrial or commercial applications. We are using alternating voltage or alternating currents. Now once we have there are a number many more advantages of AC voltage, AC currents, or DC voltage, DC currents, that you will be actually taking up as you progress through your uh, degree. As well as nowadays we are actually now trying to shift back to DC because of some other reasons. You will actually again learn that later on, why DC is now being preferred over AC. Uh, that you will also study uh, towards your final semesters. But as of now, we are we will be concentrating on alternating currents and alternating voltage. And for us, this thing is important, that generation, transmission, and distribution of AC voltage, AC currents is presently much more feasible, much more economical as compared to transmission, distribution, and generation of DC voltage and DC currents. So that's why we are using alternating voltage and alternating currents. Now, when we talk about alternating voltage, any periodic function is actually alternating. Even a square waveform like this is actually alternating. Now, why do we not have then a square function? Why are we using only sinusoidal functions? Why are we taking a sine waveform or a cosine waveform? That is the second question. Now, we can represent alternating voltage using square waveforms also, but or triangular waveforms also. Fine. These are also alternating. But then why we are taking now sine and cosine to represent alternating voltage and alternating current? Now, this is the second question. Now, sinusoids offer sinusoids have advantage over these square waveforms or triangular waveforms. So therefore, they are preferred. They have been actually the this is actually what has been used for alternating voltage and alternating currents. So firstly, producing generation of sinusoidal waveforms is much easier as compared to generation of a square waveform or a triangular waveform. Then secondly, a sinusoidal waveform is much easier to handle mathematically as compared to a square waveform or a triangular waveform. ठीक है? Sine function, cosine functions, we have uh, we have mathematically speaking uh, trigonometric equations. We have sufficient knowledge about that trigonometric equation, a number of equations that can help us in mathematical analysis of sinusoidal functions. Thirdly, uh, sinusoids are the basic functions. You can even represent a square function using a sinusoid. You can represent a triangular function using a sinusoid. You cannot represent a sinusoid by a square function, but you can represent a square function by a sinusoidal function. Fine. So this square function is actually made up of a number of sinusoidal functions. So if you add up all these different sinusoidal functions, what you will get is ultimately a square function. But a square function cannot be, from a square function you cannot get a sinusoidal function. So there were two questions: why AC over DC? We are using AC, we are preferring AC over DC because of the fact that AC is easier to generate, transmit, and distribute. Fine. So this is question number one: why AC over DC? Now, this is actually an old question, but we are still going to stick with it. Why we are using AC over DC systems? Fine. We are using AC systems because AC is easier to generate, transmit and distribute over the power lines, and also we can actually convert AC power. You can step up, you can step down the AC power. It is not possible to do that with DC systems. That's one question. Second question we have to now ask is, now we have an AC function. Now why sinusoids for AC? So as I was saying, there are two questions that we need to answer. One is why AC over DC? Why we are preferring an AC system or a DC system? We are using AC systems because they are easy to generate, cheaper to transmit, and distribute. So you are generating AC at some hydropower station or nuclear power station, steam power station, whatever. So you can generate it easily. You can transmit it then from that generating station to your substations and then to your local uh, transformers and then to your households. So that distribution as well as transmission is much more cheaper as compared to transmission of DC over the same distance, um, generating it, as well as the fact that transformers are available to us, which help us in stepping up or stepping down AC voltage. It's not possible to step up or step down a DC voltage. So a DC voltage would not be feasible for us for any residential or applications or any commercial or industrial applications. So that's one question. Second question is now why we are having sinusoids, why we are using sinusoids for AC systems. Why not any other alternating waveforms? We have different alternating waveforms. We have a square waveform, we have a triangular waveform, we have a sine function, cosine function. Why only sinusoids? Why sine and cosine are used for representation of AC waveforms, not square or triangular waveforms? So the answer is again one, it is easier to generate a sinusoidal function as compared to a square or a triangular function. It's easier to generate. Two, uh, mathematics of sinusoidal functions is much more advanced, and we can easily analyze these sinusoidal functions. Fine, mathematical advantage. And three, we can uh, thirdly, what we have here is that a sin any other function, a square function or a triangular function, can be easily represented by sinusoids. We cannot represent a square function as a sum of different sinusoidal functions. We cannot represent a sinusoidal function as a sum of different square waveforms. Okay? So you can have a square waveform like this. What it is made up of actually is a sinusoidal function, fine, plus another sinusoidal function, plus another sinusoidal function, fine. So the summation of all these sinusoidal functions will result in a square function. That you cannot do with the that it will be possible for you to show a square function as a sinusoidal function, summation of different sinusoidal functions, but you cannot show a sinusoidal function as a summation of different square functions. Uh, so with these advantages, sinusoidal functions is preferred for AC voltage and AC currents. Right? So we have to answer both these questions: why AC or DC, and then once we have AC voltage or AC current, why we are using sinusoids to show AC voltage and AC currents. Uh, And you have to also, we have already represented this Vm. V is equal to Vm cos of omega t plus phi, or you can say Vm sine of omega t plus phi. You can represent it as V is equal to Vm sine of omega t plus phi, or V is equal to Vm cos of omega t plus phi. And it is better to show it as a function of time. Vt is equal to Vm cos of omega t plus phi. Omega is the angular frequency, phi is the phase, omega t plus phi is the argument of this function, Vm is the magnitude of this function. So all these, how we can derive omega, phase, Vm extra, you need to look into that. Say for example, we are taking a simple, this is a simple example. Let Vt is equal to 100 cos of 314 t plus 30 degrees. So you have to tell me what is the magnitude of this, what is the phase of this, what is frequency of this, what is angular frequency of this, what is the frequency of this. Fine. So Vm is directly 100, omega is 314. You can also tell me the time period of this. Okay? Phi is 30 degrees. To find out f, we have to divide omega by 2 pi. 314 divided by 2 pi. Okay? So this is 50. Fine. And to find out t, we have to find the reciprocal of 1 by f. That is 1 by 50. That is 0.02 seconds. ठीक है. This is in hertz. ये volts हो गया, ये radians per second हो गया आपका. ठीक है. Phase आपका degrees में. So f equal to 50 hertz is the fundamental frequency, or what we can say is the system frequency that we have adopted in India, or actually in all of Asia. F equal to 50 hertz is the system frequency, power system frequency that has been used for generation, transmission and distribution of AC voltage. इसके अलावा F equal to 60 hertz is used in some countries like US, some European countries. Baki, most of the other countries, they are using F equal to 50 hertz as the frequency at which voltage is generated, transmitted and distributed. Fine. Yes. आपका सवाल क्वेश्चन क्लियर नहीं है, आवाज क्लियर नहीं है. फिर हाँ बोलो. हम्म. खपत मतलब बिजली की कंजप्शन फ्रीक्वेंसी पे डिपेंड होती है. फ्रीक्वेंसी का फ्रीक्वेंसी के कंजप्शन फ्रीक्वेंसी पे डिपेंडेंट नहीं है. अगेन आई एम क्वेश्चन, आवाज क्लियर नहीं है. There are actually only two frequencies that have been adopted: 50 hertz and 60 hertz. Uh, why we are using only these values, or why we are not using any other values, या फिर ये एक्चुअली डिपेंड करता है many factors पे. मोस्ट इम्पोर्टेंटली आपका जनरेशन पे डिपेंड करता है. what frequency you can be able to generate, transmit and distribute again, जो आप वाइडली यूज कर सकते हो. ठीक है, तो इसका डिटेल्ड आंसर तो अभी मैं देख नहीं सकता आपको, बिकॉज यू विल बी स्टडिंग दिस इन मशीन्स कोर्स एज वेल एज इन पावर सिस्टम कोर्स. आपको बहुत सारी चीज़ें यहाँ पे याद रख एक्चुअली इसमें पढ़नी है. फ्रीक्वेंसी पहले जनरेट कैसे होती है, किस फ्रीक्वेंसी पे जनरेट कर पाते हैं हम, why 50 hertz or 60 hertz, why we do this. One, it depends upon the machines. Secondly, frequency control जो होता है आपके पावर सिस्टम में, उस बेसिस पे आपके सिस्टम में जो पावर क्वालिटी इश्यूज होंगे वो कैसे एड्रेस हो जाएंगे, उस पर भी डिपेंड करता है. ठीक है, इसका डिटेल्ड आंसर तो भी आपको समझ में नहीं आएगा. यू विल बी एबल टू अंडरस्टैंड दिस मोर इन पावर सिस्टम्स. और जैसे कि मैं आपको ये बता रहा था ऊपर, स्क्वायर फंक्शन, व्हाट दिस स्क्वायर फंक्शन इज मेड अप ऑफ इज, it is made up of a sinusoidal signal having a fundamental frequency f. ठीक है, and then it's made up of another sinusoidal function having a frequency of 3f. Fine, but with a lesser amplitude. Then it is made up of another sinusoidal function having a frequency of 5f plus another sinusoidal function that will be having a frequency of 7f plus another sinusoidal function of frequency 9f, and so on. Fine. So you'll actually study this also in Fourier analysis, how you can generate the Fourier analysis of a square function and represent it as different sine waveforms. So these sine waveforms, uh, these sine, इनका जो amplitude है वो कम कम हो रहा है, but your frequency is uh, your fundamental frequency f, then you'll be having another sinusoidal function of frequency 3f, then 5f, then 7f. So all of these other sinusoidal functions, they are known as actually harmonics. So what are harmonics? They are actually sinusoidal functions of uh, having the frequency of multiples of the fundamental frequency. If your fundamental frequency f is 50 hertz, then these other sinusoidal functions will be having frequency of 3f, 5f, 7f, 9f, odd frequencies mostly. Even frequencies आपको available नहीं होती है ऐसे. Very rarely you will be having even frequency multiples. These all of the frequencies are actually known as harmonics. They actually uh, they are the sources of power quality issues that are present in the system. जो आपके पास अवेलेबल वोल्टेज होती है या करंट होती है वो भी प्योर साइन नहीं होती है, उसमें भी थोड़े बहुत हार्मोनिक्स होते ही होते हैं. आपने इन्वर्टर्स पे भी जैसे देखा हुआ होगा, they come they are labeled as pure sine wave inverters. So what do they actually mean is that they are able to produce pure sinusoidal waveforms without producing these harmonics. Fine, that's a separate issue. That's again a separate thing that we do not need to focus on right now. So this is about sinusoids. I wanted to discuss phasors also today, but we'll be discussing that tomorrow now. So this is one representation of alternating voltage and alternating currents. We can represent an alternating voltage and alternating current in a sinusoidal wave, in a sinusoidal form. ठीक है, तो यहाँ से from here on, what will we do? Yes. हाँ. From here on we'll be representing voltage as Vm cos of omega t plus phi. ठीक है, तो ये वोल्टेज हो गई। यहाँ से हम इसको कॉस फंक्शन ही लेंगे मोस्टली, नॉट एज अ साइनसाइडल फंक्शन। फाइन, ये तो हो गया। फेजर हम कल पढ़ेंगे। नाउ कमिंग बैक टू योर क्वेश्चन, हम 100 हर्ट्ज पे क्यों नहीं करते हैं, या वाई ओनली 50 हर्ट्ज? 100 हर्ट्ज को जनरेट करने में आपका जो मशीन होगी उसकी कॉस्ट भी बढ़ेगी, तो आप मशीन की कॉस्ट नहीं बढ़ाना चाहते हो, ठीक है, दैट यू डू नॉट वांट टू डू। द मोर द फ्रीक्वेंसी यू वांट, जनरेशन की कॉस्ट बढ़ेगी, मशीन की कॉस्ट बढ़ेगी, ठीक है। मशीन की अपनी कुछ कैपेबिलिटीज होती है कि किस फ्रीक्वेंसी पे वो जनरेट कर पाए। जैसे मैंने आपको बताया, आप एक्चुअली धीरे धीरे पढ़ लोगे मशीन में, पावर सिस्टम में, तो जितनी ज़्यादा फ्रीक्वेंसी आप एक्चुअली जनरेट करना चाहते हो तो उतनी ज़्यादा कॉस्टली इक्विपमेंट आपका बनेगा, दैट यू डू नॉट एक्चुअली वांट। तो आपको एक्चुअली एक कॉम्प्रोमाइज़ करना है बिटवीन हाउ मच फ्रीक्वेंसी यू वांट टू हैव एंड हाउ मच फ्रीक्वेंसी यू कैन एफर्ट टू हैव, ठीक है। यस, ठीक है, मैं कर लूँगा बाद में, या कल तक कर लूँगा। So sinusoids from here on will be actually representing a voltage waveform as Vm cos of omega t plus phi, or cos Vm sin of omega t plus phi, or most likely phi will be 0, or phi can be having some value. We'll be looking into that. बाकी जो trigonometric functions है hopefully वो आप revise कर लो, like you may be having sin of a plus b, sin of a minus b, cos of a plus b, cos of a minus b, sin of omega t plus 90, sin of omega t minus 90, cos of omega t plus 90, cos of omega t minus 90. All those things you should revise. Um, hmm. So that will be all for today. We'll be studying phases tomorrow.